Thank you for coming. And my name is Professor J.C. Chow. I'm with electrical engineering. First thing, take out your iPhone and smartphone, turn it to silent. I wait here until you finish it. Very important is a respect to everybody else here. Second things, if you have class at 7 o'clock and you are going to leave right at 7 o'clock, I suggest you to move to the back or to the side so you don't walk right in front of everybody to exit the room. That's not very respectful for everybody else here. So if you are planning to leave early, please move your seat to the back. Okay. And welcome everybody for our distinguished speaker series for college engineering. And our speaker today is Professor Abbott from University of Adelaide. And he's going to tell you where Adelaide is when he starts his talk. And Dr. Abbott is one of my idols. And in the academic sense, that he's an IEEE fellow, and he's with the editorial board or proceeding of IEEE and +1. For young students here, just start your academic career. These are great honor position. And he started several research groups at University of Adelaide, including T-Ray group, which is actually a very hot name. He named it for terahertz research. And he also started the Center of Biomedical Engineering and the Center for Integrated Circuit group. And the reason I say Dr. Abbott is my idol is not because he delivered more than 100 invited talks at MIT or in Europe, in Asia, all these high caliber institute, not because of that. And it's not because he published 700 papers and now it's almost 100. His group is publishing one journal paper every week. And the paper he published are covered all of the topic like optics, electrical engineering, material science, metamaterial, I don't know how to characterize that, terahertz, MEMS, inside vision, like a bio-inspired system, high-speed electronics, and now he's working on research in energy. So all these topics are very different and multidisciplinary field. And this is not because I admire him. And he also published a paper that in the end you'll be quiz on. Sorry, no. This is in proceeding on IEEE. For the first year engineering student, I encourage to download, to read this paper. It's a very, very good paper to know what our energy need is. As I mentioned that he's my idol, not because he published very high caliber books. He published one for statistics, and he published one paper for terahertz imaging, which can be used for breast cancer imaging. And the reason Dr. Abbott is my idol is his introduction in his website. And for young students, I do recommend you to go there. The first sentence, he said he's somehow backward dopey, and that's, I share something with him, and I think if he can be successful, I can be successful some days. And this is a very inspiring article, and I recommend students to go read. And at the fun time, at a pleasure time, he writes a fun book. He writes a book called Quantum Aspect of Life. If you think about it, our body is based on atom. Atom follow quantum mechanics. Why shouldn't human also follow quantum mechanics? Very interesting book to read. And he also, in his free time, he solved murder mystery. If you Google these 3 words, you will come out with more than 360 articles about this murder case. This murder happened in 1948 at Adelaide. And Dr. Abbott is trying to solve it with engineering perspective, using signal processing to analyze the secret code in one of the evidence, and using DNA to find out who this person is. I blocked the photo here because this is that dead man's photo with drawing, so it won't spook everybody. He collected quite a lot of evidence in his own website, so this is still remain unsolved, but maybe one day it will be solved. And he just done so much, so when he traveled in the airplane, he write a book on his iPhone. It's called Weak Dictionary, and he give new meaning, new definition to the words we use every day. So by now, if you don't know, he's my idol, and I think he's very, very successful. So I'm going to borrow something from his book to describe him. Dr. Abbott, in my opinion, very successful, and successful means that he knows how to channel his obsessive compulsive tendency to something useful. So for everybody there with OCD like me, we have hope in the future. So now, without further ado, let's welcome him.
Thank you, JC, for that very warm welcome. Thank you all for having me here, and the Dean for inviting me. I have been to Texas many times before, but this is my first time at this particular university, so I'm very honored to be here. So as the first slide suggests, what I'm going to talk about is the world's energy needs. How do we supply the world's energy in the future? The perspective I'm going to take in this talk is one of resource limitations. I'm going to examine how long each energy source could possibly last. So I'm going to do a typical thing that engineers do. I'm going to take things to their extreme limits. I'm going to ask a hypothetical question. I'm going to say, what happens if we run the whole world of just one energy source only, then the other? We'll do each one by one, and we'll see how it falls over. And so we'll see which energy sources are the ones that go really into the long term, and where perhaps the long-term research perspective should be. Now, I know I have many colleagues in this room who are working on some of the things that I will show are short-term, so I hope they won't shoot me at the end. But I just want to say about them, their research is still useful, because I still believe all research is interconnected and we all learn things. And there's always niche areas where you need different things, and you also need energy diversity. So I don't want to demean some areas that are represented here, but what I will show in this talk is where the main possible future thrust should be in the future. So just a quick introduction. This is my university, University of Adelaide. We started in 1874. That's the building where I work. We have 3 Nobel Prize winners that we actually educated as students. Those are the 3 guys on the top, and some other famous guys on the bottom that you may have heard of. I come from an EE department. That's our department, started in 1946. This is just a fun slide. This is me. Oops, sorry, I've gone too fast. This is me here on the bottom. This is my PhD supervisor, and this is his going on. And if you've only got to go back 3 steps, and you get to the guy who discovered the electron. So you should have fun tracing your one as well with your PhD supervisor. You never know where it goes. So the question about this talk is, how are we going to generate power in the future, and how can we do this in a clean way that isn't going to create problems? The problem is, quite often when analyzing this whole thing, there's a lot of disinformation out there. Lots of people say different things, and there's a lot of chasing the snake's tail when you try and examine the whole issue of energy. And so what I'm going to try to do in this talk is simply to cut the snake and try and make some sense of it. A take-home message I will be giving is large scale. The solution is going to be to go into something in very large scale. There's no point doing something very small in the energy business. The great thing about engineering is, as an engineer, you only need to be 80% right of the time. You don't have to be 100% right. You can be roughly right and go in the right direction, and then you can work 20% of the details out along the way. And so you will make some mistakes along the way, and so we will, in the whole energy scenario, I'm sure we will make mistakes along the way, but they will be worth it because they will get us to the end. Now, I don't want you to think I'm some energy expert. As JC showed you, I'm kind of interested in lots of things, but my main, I think to characterize what my main area is, I'm interested in multidisciplinary engineering and complex systems. And so I'm going to view this whole energy debate from that viewpoint. I guess if you take this definition of an expert, unfortunately, I am sadly an expert by this definition. But I'm definitely not an expert by this definition, because I will be showing you how it can be done. Just a few quick acknowledgements, those who have helped me with this work. Special acknowledgements goes to these guys, because Ricky was the student who helped me with some of the calculations early on in this work. And this guy gets a special acknowledgement because he's almost 90 years old and he's still active, and he inspired me to get into this area and to think about it. And at his age, he's still creating energy spin-off companies and stuff like that, and he still travels and flies on aeroplanes. He's just amazing. I hope I can be as active as him at that age. So this thing about this talk is I'm not going to show you any new science. I'm not going to show you any new energy sources that you don't know about already. But what I'm trying to go and do is to help to package them in a harmonizing way to make sense of them all. So that's what I'm going to do. If you want to follow up the details of this talk, because you know I can only brush over them in half an hour or so that we've got, I encourage you to follow up the paper that was in this issue of Proceedings of the IEEE, where all the details are there. So what is the problem that we need to solve? The key problem is the world energy consumption is 15 terawatts. We consume 15 terawatts. What does that mean? It means we suck 15 terajoules every second. Every second goes by, another 15 terajoules just got consumed. That's the world as a whole. That's mankind's energy consumption, electricity, gas, petroleum, the whole thing. So the big question is, one thing we've got to start off and make clear in our minds, especially for the students here, is how much really is 15 terawatts? Is that really a lot, or is that a little, what is that? So let's go through this step by step. So first of all, how much is a watt? Well, that's a typical flashlight. What's a kilowatt? That's a jug, an electric jug. 3 megawatts might be something like this diesel train. 50 megawatts example is the power consumption of all the computer servers at Google headquarters put together. So that's amazing that Google is like a few trains put together, but it gets the job done. What's like a gigawatt? A good example, this is energy generation now, because I couldn't find an specific example of consumption at this level, but the Hoover Dam is a 2 gigawatt dam. What about a terawatt? What is that? So this is now getting to the level of the human consumption. Remember, the human consumption was 15. So it turns out that all the photosynthesis that goes on in the whole world is 90 terawatts. So all the leaves in the world absorb about 90 terawatts of light and get converted to help those plants grow. So this will explain, this slide explains why in this talk I skip over biomass or biofuels, because basically if the world energy consumption is 15 terawatts, then I've actually got to burn everything in the whole world, and the actual energy efficiency of that will be quite small, and it will end up as something like less than 1 terawatt. So biofuels, at the very most, can only scratch the surface of the huge energy pie. So it's not appropriate for me to go into that talk, but it still has valid niches. For example, making biofuels out of trash is still a useful thing to do. Here's an example of 200 terawatts, Hurricane Katrina. I'm not suggesting you would ever want to harness that, but that's an example of that awesome amount of power. And of course, it doesn't last that long. A picowatt. Oh, we have a picowatt happening here right in Texas. It's this laser. Now, you might think, hey, how can a laser suck more than the whole world's power consumption? But don't forget, this is on for less than a picosecond at a time, so it's okay. What's a yottawatt? 10 to the 24. This, in 1963, the Russians let off a nuclear fusion bomb, and that was 5 yottawatts. There's a picture of it there. And then we run out of fancy Greek names to describe the power. And basically, all the illuminance of all the stars in our galaxy is about 10 to the 36 watts. And physicists tell us that the maximum amount of power you can possibly have is 10 to the 52. You can't go any higher than that. There's actually physical limits that stop you doing that. And that's called the Planck power. And if you try to even get a quarter of that, according to physicists, I don't know how they came up with this quarter, but they said you'll create a black hole. So we don't want to do that. But this does illustrate some important principle here that, there is just so much power out there in the universe coming from these stars. And the 15 terawatts is just a tiny blip. So our consumption is very small compared to what's potentially out there. One thing I will brush over in this talk is the idea of energy conservation. You obviously got to conserve energy better as a society in the future, but that's not what the talk is about, but we'll take it for granted that we do need to do those things more and more in the future to make sensible use of our energy. Just as an example of how energy consumption can just get carried away is, let's just hypothetically say that everybody drives a car for 1 hour a day. Let's pretend we let everybody in the world do that, and there's 5 billion people in the world. You can, and let's just say everyone's driving an average car engine of 50 kilowatts. You can do this calculation on the back of the envelope. You should find that sucks 10 terawatts. So that's already nearly the world's whole energy consumption right there. So, and this is another problem with the whole energy pie scenario, is that some things are simply not scalable. And so this is something we have to keep in mind as we go into the future. So let's examine all the different energy sources that we use today. And so a common one is oil. And there was a guy called Hubbert, an American guy in the 50s and 60s, who made this prediction that oil will peak. And it's looking like it's doing that. Another key thing about oil to bear in mind is that it has geopolitical consequences. And here is the map of the world redrawn by size of oil. And as you can see, it's got a very uneven distribution and creates problems as a result, which we all know about. Now, some people like to suggest that, oil is limitless and it lasts forever, especially you hear politicians saying that. You don't hear scientists saying that. So what I want to show is why the politicians are actually wrong and they haven't done their maths correctly, is let's just, as engineers, calculate a crazy hypothetical upper bound for the possible maximum amount of oil that could ever be on this planet. And so what you can do is take that figure I showed you for all the photosynthesis that happens, which is 90 terawatts, and integrate that over 3.7 billion years and pretend that plants were just growing continuously at the same rate all the time. And let's pretend that's all instantaneously all converted to oil. So that's a crazy assumption, but you know that oil can never be less than that then. And let's create a crazily high conversion efficiency of 1%. Reality is it's probably a millionth of that, but let's make it crazily high. And you can do a little rough back-of-the-envelope calculation and show that the maximum amount of oil you could ever have using crazily high assumptions is 0.3 of the planet's volume, which is basically over twice the total amount of water on the planet. We clearly do not have that amount of oil. But if we did, how long would it last? Well, a typical annual growth rate over the last decade that we've been getting in our oil consumption, it's actually dropped at the moment because oil's getting expensive, but what it used to be was 1.3%. And so if we take that annual growth rate and calculate from that starting amount of oil, it turns out, because of the doubling effect that when you get something exponentially growing, it turns out that that amount of huge amount of oil would only last 1,200 years, which isn't really all that long for such a massive amount of oil. So when scientists today say that oil that we do have is only going to last 40 years, you know, that sounds about right when you put it in that perspective. Another way to think of this oil issue is one thing called the 1 minute before midnight effect. So you just think of numbers doubling, and if you say, look at the number 32, it's bigger than the numbers before it. And similarly, number 128 is always bigger than all the numbers added together before it. So what that's saying is that, have I got this on the next slide? Yes, it's saying if you take an annual growth rate of 1.3%, which is what we typically had in the past, means the doubling time is of the order of 70 years. So what that means is from now to the next 70 years, we've got to find an amount of oil that equals all the oil added up since we first discovered oil, right from the beginning. That's a huge amount of oil. We clearly haven't got that amount of oil for the next 70 years, so it isn't going to happen. Another proof that oil is running out is if you look at the discovery of giant oil fields. They peaked back in the early 70s, and they've been declining. So the discovery of new oil isn't keeping up with the demand for new oil. Similarly, if you examine things like coal and natural gas, they follow similar types of curves, but will last longer. But then we also have to ask questions about their environmental impact. Hubbert, in the US Senate committee in 1972, wrote this beautiful graph. He said this is 5,000 years on this end of the axis and minus 5,000, and this is our fossil fuel consumption that's available to consume, and he shows there's just a little delta function on that time scale. So that kind of puts it in perspective. So my answer to politicians who say oil will last forever is I like to say to them, yeah, oil does last forever if you don't use it. Okay, so what about nuclear fission? Will nuclear fission save the day? Is that a possible path ahead? So for those of you who want to delve further into the details of my calculations here, I direct you to this article here in Proceedings of the IEEE. So basically, what would it be like if we scaled up nuclear power to power the whole world? And let's pretend that nuclear power powers the whole world and nothing else. What would that look like? Well, at the moment, what it looks like is we have 440 reactors in the world today. Give or take a few, you know, every time one blows up. I can't keep count of them at the moment, but it's plus or minus, you know, 5 or something. Now, to match the world's power power consumption, you would need about 15,000. You'd need to scale up to 15,000 all of a sudden. Now, Jacobson from Stanford, in this article here, calculated the average nuclear footprint of the world. So what he did is he took all 440 nuclear power stations, added up their area they take, added up the area of the exclusion zone and the processing plants and all the associated things you need to do to make nuclear power, added up all those areas, and he came up with an area of 20 kilometers squared. Whereas for, say, solar thermal power, for example, using solar energy, that's the footprint. And so you'd probably have to multiply this by about 5 to make these two figures comparable. And so solar does end up being a little bit bigger than nuclear power, but not much more. So it's not giving you such a big saving in footprint at the end of the day. So bearing that in mind, let's look at where all the nuclear sites are actually in the USA. And in the USA, you have about 63 commercial reactors that are actually operating today. And if you were to pretend and say, hey, let's make the whole country nuclear, you'd need to go to about 4,000 to do that. And so the question is where would you locate them? You already have so many dots. Where would you find another dot somewhere where you're not going to get a lawsuit and all those kind of problems? So it is challenging to try to even put 100 more dots on this map, let alone 4,000 dots. If anyone can get that map out and put 4,000 dots on, email me. I'd like to know how you did that. Then there's the problem of nuclear waste. The nuclear industry says, hey, no problem, we just put them in these yellow barrels, and we have guys with yellow hats to protect you. But that's a bit like saying the Titanic will never sink, and we know what happened there. And it's a political hot potato, nuclear power. As you know, anything you do in life that's irreversible always has implications for future generations. Something they don't tell you about is cracking. The nuclear vessel actually cracks because there's high energy neutrons. The metal vessel that contains the reactions is made of metal and so corrodes as well. And so you get this cracking over a period of time. It takes 40 to 60 years to do that, but that's the reason why you close the nuclear station down in the end. And closing it down is very expensive. It costs almost as much to close it down as is to open the nuclear station in the first place. So there's hidden costs there. And the consequences of accidents are quite costly as well. And this is a famous accident that happened in the USA not so long ago. Now the accident rate at the moment is there's 70 reported incidents per year. These are just minor things, like pipe leaked or something like that. And if you were to scale those up, that would end up as 5 small incidents every day. So it won't take long for that to develop into a major incident. And I calculate in the paper that you would be looking at one major incident every month somewhere in the world if the whole world had 15,000 reactors. At the present rate of consumption of uranium, it looks like it's got about an 80-year life based on, you have to look at the concentrations of the ores. And when you go down to a very low concentration of uranium ore, it becomes extremely costly to extract that. So the nuclear lobby says, okay, the answer to that is we use fast breeder reactors. And a fast breeder reactors is something that reutilizes the spent fuel and breeds further usable fuel out of that. And they say that it can last about 60 to 80 times longer if you do that. And so if you do that calculation, multiply 60 by the 80 years, it blows it out to 4,800. So you think, not bad, that's pretty good. And then extracting uranium from seawater. By the way, seawater has lots of uranium, very low concentration though, but if you could do that, you would have enough to last you over 10,000 years. So when you hear people say nuclear power lasts forever, they're kind of right based on these calculations of 10,000 years. So that's good, and that's forever for us, for our lifetimes at least. But, so let's actually quickly look at that calculation. This is the total volume of seawater, and this is the uranium content. It's 3 parts per billion in seawater. It's a very low concentration, but because there is so much water out there, it actually works out that there's, 3 times 10 to the 10 kilograms of usable uranium out there in seawater, so it's huge. And that's the energy content in terajoules. And at 15 terawatts, that would last you nearly 6,000 years. So that's pretty encouraging. And then if we include a fast breeder reactor, that's 300,000 years. So that's great. We have a nuclear utopia here. But what has been ignored here in these calculations is the rate of extraction. Okay, so you've got this total amount of uranium, but what about the rate at which you can extract 3.3 parts per billion? I could have an infinite massive uranium on the next star in the next galaxy, but the rate at which I can get it is 0. Okay, so rate is an important number that has to be taken into account. And so what you can do, for those of you who do a bit of chemical engineering, this is called the mass balance equation. You'll recognize that. That's concentration. This is water flow rate. This is your volume. It's not a simple exponential as you would expect, because as the concentration lowers, as you extract the uranium out of the water, the flow rate has to go up. So sticking that into the equation and recalculating, you can solve this differential equation very simply, and it comes to 5,700 years as you would expect in total. But what you then need to do is integrate that and find over a reasonable time, like say over the next 30 years, what the volume of water you would have to process is. What is the total volume? And it turns out that it's about of the order of 10 to the 15 cubic meters of water, and that's a huge amount of water. That turns out to be 6 times all the outflow of all the rivers in the world. It's huge. It's obviously an impossible amount of water to process. You could never do that. So the moral of the story is what works on a small scale might not necessarily scale up to work at a very large scale. And that same story is true for things like, say, growing crops for biofuels and stuff like that. So another question you have to ask with nuclear power is, what are nuclear stations actually made out of? It's not just concrete and steel. It turns out they're made out of, the steel has all these sort of exotic materials associated with it. And there's various materials used for controlling the reaction around the rods of the nuclear reaction. And so the question is, how long do these metals last? How long do these metals last? And we've got to ask questions about all the toxic chemicals and acids and solvents and high temperatures you need to extract those elements from their ores. Now what's interesting is if we look at, say, all the amount of beryllium we have and niobium and hafnium, etc. we have in the world, and what their present annual growth rate is in production, and this is across all industries, not just the nuclear industry, because remember, we have to use these elements for everything, not just nuclear power. It turns out that the extinction times are actually less than for oil. So to say that nuclear power is the answer to the oil problem is clearly not correct, because although that calculation might work for uranium, it doesn't work for the things that you make the nuclear reactor out of in the first place. Another thing is that these elements, once you use them in the nuclear reactor, you can't reuse them. You've lost all your hafnium. You have to bury it because it becomes radioactive for thousands of years. And so there's a question here of elemental diversity. You're destroying your elemental diversity of elements on the planet if you let nuclear power take over. So there's two types of nuclear utopian. There's the nuclear advocate, there's the nuclear utopian and the realist. A utopian is the guy who says it will last for 300,000 years, but there's some things that haven't been taken into account there. And the nuclear realist might say, okay, we need an energy mix, maybe we should have 1 terawatt of nuclear power in the world. That might be more reasonable, but that's for future generations to decide from the other aspects of safety, etc., etc. That's just a joke slide. Possibly a justifiable use of nuclear is when the sun expands in 1 billion years or so and fries the Earth, we will all have to leave the Earth somehow, and we might need nuclear energy to be able to do that. Let's look at some other forms of power very briefly. So hydroelectric power, renewable source, that actually supplies about 20% of all the world's electricity. So it's a good source of power that's renewable. The catch is there's not much room to expand it much further. Perhaps a little more, but not too much, because there's a limit to the number of waterways you can build these dams on. There's a physical limit there. Another thing is wind power. It's great. It's become very fashionable. Wind power is really taking off around the world. Many countries are investing in that, including the USA. Germany's really big on it. But what you have to think about with wind power is, where does wind come from? What is wind? Wind is just sunlight that heated the ground, and the ground heated the air and created convection currents, and that's what wind is. So wind power is basically solar power with a 99.9% efficiency loss, conversion efficiency loss. So if you're in a really hot place like Australia here, it pays to use a footprint like this for solar power rather than wind power, you would have thought. Of course, there is an argument for energy diversity and having both, but I'm talking about the big vision. What should we invest in the bigger way? Then there's wave power. I'll come to that later. I'll show you some figures and show you that's actually quite small, the total amount of wave power you could possibly generate. Then there's the question of nuclear fusion. Will that save the day? And my answer to that is no, and you'll see the details in the article. Basically, nuclear fusion will suffer the same problem of neutrons embrittling the metal vessel, and you having to close down the fusion station every 50 years, and all those exotic elements that the vessel are made of to keep that vessel strong and stop it embrittling will be buried, and you'll destroy your elemental diversity, and you'll run out of them pretty rapidly. So that's the nuclear fusion problem is still stuck with the same problem as nuclear fission. But hang on a minute. Here's the surprise. Everyone actually has a nuclear fusion reactor in your backyard at home. Where is it? Of course, it's the sun. That's God's own fusion reactor. But, you know, before I got into this, you know, I thought, solar energy, come on, how much can you get out of it? Is it enough to power New York, Europe, half the planet, or 10,000 planets? It's a little quiz. I'm sure most of you know the answer. It turns out it's enough to supply 10,000 of our planets with similar population, because the solar power that hits the whole planet is in the order of hundreds of terawatts. It's hundreds of thousands of terawatts, sorry. So it's huge compared to 15 terawatts, which is what we presently consume. Now, you've got to take into account some reflection from the clouds and absorption absorption from the clouds and reflection from the ground. And it turns out that you lose half the power, but that's okay. We can still run 5,000 planets. So 5,000 is the key number, and the question is, why is it that you don't hear this number 5,000 from the lips of every politician in my country and your country and all the countries? I think all politicians have got the same problem, whichever country they're from. We have them too. And I think that's probably the answer. I think it's our job as engineers to try and get the message out there and express it very, very simply, because that's all politicians can understand. Simple. Okay. Now, I was going to show you some figures. So here's the total surface solar energy that hits the planet. Then here's all the solar energy that hits the deserts of the world. And if we pretend we call this 100%, that means all the desert energy is, solar energy is 9%. And then when you see all the other renewable sources like geothermal, hydroelectric, tidal waves, coastal waves, all that sort of stuff, it's absolutely tiny. And if you add up all these alternative sources, they come to less than 1% of solar. So solar is the big guy. This is the take-home message. And the question is, how long will that last? Well, we know the sun's going to be out there for 10 billion years. But in 1 billion years, we'll all be fried because the sun expands and kills us all anyway. So we've only got to worry about using it for the next maybe 500 million years, because we'll have to leave the planet by then. So where are the best locations for solar energy? So these are all the hot spots around the world. And you've got some great little hot spots around here in the USA. So you've got the potential. You've got deserts in California and Arizona, and it's pretty hot here too. Now, are solar cells the way to do this? Well, solar cells are great for pocket calculators. And, you know, they're becoming pretty cheap, pumped out of China, and the price will keep coming down, and so they'll be great for your rooftop, for offsetting a bit of your electricity bill, etc., etc. But to actually supply the whole world's energy with these guys doesn't work, and I send you to my paper to see that. I calculate the total area of solar cell that it would take to supply the whole world and all the chemicals you would need to actually do that. And you actually run out of all the world's arsenic dopant to be able to do that, for example, just one example out of the thin air. So you'd totally steal all the chemicals you need for the semiconductor industry and making computers. So it's obviously infeasible to take it over in a completely big way. But you could maintain an energy harvesting niche with solar cells. So here's the solution, is to use what is called solar thermal, because solar thermal just uses mirrors and focuses sunlight on a fluid, creates steam, runs a steam engine or steam turbine, creates power. And here's one of the most successful ones in the world, is actually in California. Successful because it's been going for 20 years and hasn't had a problem. And one of the secrets to their success is what they've done is they've taken a very pragmatic approach to it, and they've evened out the intermittency of solar and the fact it doesn't work at night by just powering off natural gas when the solar's not on. So it's a dual natural gas solar system, and it pumps out this even amount of 350 megawatts. And I think this is probably the way to go in the short term for the world, is to use dual natural gas and solar thermal. And one day we will run out of natural gas eventually. It may be a while for that to happen, but when we do, hopefully by then we will have brought online various energy storage mechanisms to overcome that. And here's other ways to do solar thermal. This is one in Spain, this is Australia, and another Australian one, this is California. This is the world activity here. Coming to the end of the talk now, so I'm just going to whiz through these last slides just to give you a feel. The Germans are doing this 400 billion euro project to start actually building them in Africa, because they don't actually have enough sun in Germany. And they'll spend 500 billion of that on transmission lines to bring the power over to Europe. Now, we need storage and distribution. So I'm going to skip over that and just direct you to this special issue of Proceedings of the IEEE, which analyzes all the different storage options. So that's all there for you to read. One way of storing is to split ammonia, but the question is, where would you get all that ammonia from? Another a simple idea is just to split water and use the hydrogen. The great thing about that is it's a closed loop cycle, because when you burn the hydrogen, you go back to water again. And water goes naturally back into the environment. So I'll just skip through all this because we don't have time, but it's showing you that we do ship 75 million tons of hydrogen every year anyway for the chemical industry, so it's well known. Fuel cells have a problem in that they do have extra chemicals and catalysts and things that you have to use, and they're fragile. So a suggestion I'm putting forward is combustion engines, and they do exist. These are combustion engine hydrogen vehicles. This is in Berlin, a bus. This is in the USA. There's a Ford combustion van. There's a Japanese Mazda. This was done in Florida. This is showing what happens if you set fire to a car with gasoline and set fire to a car with hydrogen. It's safer than you think. If you're the driver here, you die. If you're the driver here, you're still smiling. Now, only in America would you do an experiment like this. They felt it necessary at Lawrence Livermore to shoot this hydrogen canister with armor-plated bullets to see if it would blow up or not, and it didn't. And this is what happens if you furnace the hydrogen tank at 1,000 degrees centigrade for an hour. And also BMW's fiberglass tank for hydrogen didn't explode either. So, and you know, hydrogen's pretty safe. Here's a space shuttle showing you hydrogen flames, and this is a hydrocarbon flame. And as you can see, the illuminance is much lower, so there's less secondary damage from hydrogen burning. The Russians in '88 actually made a plane that runs off hydrogen. It wasn't economically feasible because it turned out that natural gas was much cheaper in those days. It's kind of taking off in the US. You have hydrogen stations in quite a few locations around the States. Here's one in DC. Here's all the guys in Europe. There's one in Munich. This is in Asia. There's one in Beijing. Notice the hydrogen BP sign. Australia, we're really bad. We just got one. I'm disgusted with my government. So to supply the world's energy needs, you need about 500 by 500 kilometers. That's kind of like the area of a whole state of America, an average size state. To actually supply the whole of America, you probably need a footprint the whole size of Washington, D.C. or something. But hey, that's not bad. So bottom line is nuclear power has hidden costs, but solar hydrogen has hidden savings. For example, when you burn the hydrogen, it goes back to water. And in some countries, you actually need that water. You can reuse it, that clean water. So there's a whole bunch of research that still needs to be done to kind of bring all this thing into realization. So those are some suggested research areas. One thing that might be a surprise to you is that, hey, focusing mirrors on a fluid and just creating steam, hey, that's not very high tech. Weren't the Egyptians doing that thousands of years ago, something like that, or the Greeks? We're engineers. We're supposed to do high-tech things, But what I want to try and bring across to you to get out of that mindset is to realize that high-tech systems are very ordered systems, like semiconductors are ordered. And that means you've had to put energy in to reduce their entropy. What happens at the front end of an energy-generating system gets very hot, and you have lots of entropy. So there's no point putting a very high-ordered system in front of something that's very hot and is going to increase the entropy. You're going to reduce either things' reliability or its efficiency. It's not the thing to do. So that's why nuclear power stations and solar cells are not the solution for the big picture. They're the part of the picture, but the smaller part of the picture. So you can't put a high-tech system into a high entropy state. So the message I want to give you is use something very low-tech at the front end and do all your high-tech stuff at the back end. The high-tech stuff is in all the processing and the control systems and all that stuff to manage it. The front end should be low-tech from an entropy point of view. So here's thermal solar versus solar cells. Solar thermal, centralized power. Solar cells still will have a niche in distributed power, distributed energy harvesting. Energy diversity, you want lots of sources of energy to create stability and security. You don't want necessarily everything to go in one basket. So possibly 70% solar thermal in the medium term. Maybe in 500 years you will be forced to go almost 100%, but because we won't have anything left, but that we might have to live with that when the time comes. How to get started? Remember Henry Ford when he first made his car? There were no roads. There were no gasoline stations. People had to go to the pharmacist to buy gasoline in a little tin can. You went to the pharmacist, not the gasoline station. So you've got to think outside the box about getting started. These are some of the things you might want to do in a society to get started. In the same way that cities grew up when the steam engine went through them and you created stations and populations grew around them, maybe new civilizations will grow in deserts, in desert oases around where you build your solar thermal farms. So here's a quick bottom line to finish up. Here are the abundance of all the elements in the Earth's crust, and here's their atomic number. The things you need to do solar thermal are in the high end, and the things you need to do nuclear power tend to be in the lower end. And notice there's a huge, because it's a logarithmic scale, you're talking about a factor of over 1 million there. This is one of Hubbert's favorite curves. This shows you what happens if you've got an exhaustible resource. This is unlimited exponential growth, which economists would like you to have, but doesn't exist in reality. This is what happens with a renewable resource. You can actually exceed the exhaustible resource, but when it comes to its limit, it doesn't go down. It stays flat. That's the thing you've got to make politicians understand. They don't get that. So just to finish now, a couple of quotations. Thomas Edison here, he said, "I put my money on the sun and solar energy. What a source of power. I hope we don't have to wait until oil and coal run out before we tackle that." Then Hubbert, another US scientist, said, "Our ignorance is not so vast as our failure to use what we know." And this is the thing that's holding us back. This is ironical because this is a scientist that discovered things like deuterium and tritium that is used in nuclear power, and he himself said, Australia can get all the energy at once from the Simpson Desert, that's just one of our deserts, if only it gains the political courage to do so. And it's probably true of all governments. So that's the end of the talk. If you want to follow up the details, here's the reference of the paper. Thank you. Yeah.
Talk about biomass and deriving from biological sources. Have you ever taken like one of these things and drilled really, really deep down into it? I know there's a bill in the United States that says so much of ethyl alcohol production has to be from direct cellulosic conversion. So if you're taking a process like that and really drill deep down into it, I mean, I see your calculations for biomass in general.
Yeah.
But I'm trying to take a specific.
Yeah. No, I haven't done that. The objective of the exercise here was just to see how all the power sources compare in scale and where really is the huge scale. I couldn't find that for biomass. But having said that, I still believe there's a niche for biomass, especially biofuels that are made out of trash. I think is a good way to go. Yeah.
Since I've been working on this stuff for about 30 years, one of the things that popped up in my recent studies is what is called the energy return on energy invested ratio.
Oh, yeah.
Since the 1930s, we were working at a roughly about 100 to 1 ratio, 100 barrels of oil for every barrel we used to get it out.
Yep.
We're now down to 3 to 1 because of fracking is so expensive in energy.
Yep.
I'm listening to some of these people out in West Texas using processes is going to drop it down to about 2 to 1. The problem is when we hit 1 to 1, we stop using that source as an energy source because it's now consuming at the same rate we're using to get it out of the ground.
Yep.
My numbers indicate that we're going to hit that roughly about 2022.
Very interesting. Have you published that?
No, but some people who have. But nobody bothered paying attention to it because it was the Energy Information Agency who put out the curve, and nobody paid attention to it, including people on Wall Street who I've been tracking. And they just keep looking at it, and they don't understand that you don't talk about we're producing more oil than Saudi Arabia, because by 2020 we're going to be producing a whole lot less oil.
Very interesting. I'd like to see the reference if it's available. Oh, cool. I'll talk to you afterwards.
1 paper a week. One question from the students? Okay, great. Dr. Abbott will stay here for another 30 minutes. And let's thank him again. And this is Dr. Hubbert.
So we would like to give you a little token of appreciation for traveling all the way from Australia to come and see us and to deliver a very enjoyable lecture. Thank you very much, Derek. Thank you.
Merci beaucoup.
Thank you all for coming.
Will I be able to get this through airport security?
Maybe not.